Good. Good start?
Go for it.
Thanks. All right, so my name is Cameron. I'm going to be talking about Effectful software contracts today, which is work done with Christos, Dimoulas, and Matthias Felleisen at Northwestern and Northeastern, two different places, very important. So this is an effect handler session, but not a contract session, so I maybe want to give a little bit of a background on contracts before we start. So one maybe broad question is, what are contracts about? This is a question probably anyone who studies contracts is going to give you a different answer. I will give you one possible answer, which is contracts are an approach to specification, which takes the philosophy that specifications are code. Okay, so here's a concrete example of that. Suppose you're writing a cryptographic library. So say for generating RSA public-private key pairs. And it's a function that takes in a func that's going to give you a pair of random prime numbers and gives you back a func that's going to generate key pairs. Okay? So here's a bit of pseudocode for the contracts for that function. And you don't have to read the whole thing, but I want you to pay attention to this part here. Is prime, okay? So in the contract world, this is just a regular predicate from the host programming language, okay? And it may come from the math library, and the programmer can just use that normally. And this is really quite convenient. We get a really expressive specification that's easy to write down, and get to reuse code that is in the host language. So of course, this is a bit of a trade-off compared to a type system. So typically in contracts, we're checking these things at runtime, but it's really easy to express very rich specifications. Whereas in a type system, you may have slightly less rich specifications, unless you go to a more sophisticated type system. But you get those statically. So for the rest of the talk, I'm going to assume that we'll be checking these at runtime, although there are certainly ways to check contracts statically as well. Okay, so that's a bit of background. So is prime is code, and of course code can have effects. So that means contracts can use effects as well. And we might just try to ignore that and say, oh, well, maybe that's not that useful. Or it might end up using them accidentally. But actually, in this paper, we're interested in contracts that use effects intentionally. And it turns out that it's actually quite useful to use effects in contracts. And we did a bit of a literature review, and we found actually quite a few papers that did so. So what's an example of a contract that's going to use effects intentionally? Here's one example from a paper from quite a few years ago about doing interop between two languages. You can imagine ordinary ML. And a variant of ML that has an affine type system. Okay, and you want to do sound interop between these two languages. Okay, so to do sound interop between the two languages, you want to make sure that when you have values that flow from the ordinary ML to affine ML, that it's not going to violate the invariance of your type system. So you want to ensure that if you have a function that goes from ordinary ML to affine ML, that you're going to use it at most once. And that requires a dynamic check of that property because, well, this is an interop setting. Okay, and in this scenario, that dynamic check requires state because you have to keep track of whether or not you've applied the function in the past. So you have a bit of state that's going to keep track of that. That's an effect. Okay, so that's one example of where you might use effects in a contract. And there's a bunch of others. And actually, there's probably more than what we've found here. This is just a selection that we considered in this paper. Okay? Now, people have done implementation work. They've studied specific instances of contracts that perform an effect. But what about a theory for this? Well, what you could do is you could take a traditional model of contracts and just simply add whatever effect that you want to it. So if you want state, you can take a traditional model of contracts that's pure, add state, and say, oh, we're done. And you could certainly do that. But what's going to end up happening is, well, you might violate some assumptions. So one question we can ask is, should contracts use effects in an arbitrary way? Or should there be some constraints on the kinds of effects that contracts can use? And I would like to argue here that contracts should only use effects in a reasonable way, okay? Which is not very precise, but we can think maybe more precisely about what does it mean to be reasonable? What does it mean for a contract to use effects in a reasonable way? Okay, so informally, contracts, well, what's the role of contracts in a program? The point of a contract is to ensure that your program does not violate its specification, okay? So to raise an error if it detects that something has gone amiss. The purpose of a contract is not to do any really useful computation. So it shouldn't really interfere with your program proper. All right? So that's the informal way of putting it, that your program and the contract have two separate roles, even though they're both at runtime. But how do we say that a little bit more formally? What we can say is that if you have a program with contracts in it, and it evaluates successfully, so it terminates and it runs to a value and not an error, that should mean that when you erase the contracts, it's going to run to the same value, always, which means that the contracts are not sort of interfering with your program. So we would like this property to hold of whatever model that we come up with for contracts that use effects. And of course, if we just do the naive thing, we take the pure model of contracts and we add whatever effect to it, you're not going to get this property. It's just not going to hold naively. So the purpose of this work is to construct a model that we can express all of these systems in where erasure holds. And this is the goal and what we've achieved here. Okay, so how do you do that? Well, the session is a bit of spoiler because effect handlers, right? So to reiterate, our goal is to have a unified model satisfying erasure, and that theory, moreover, should be implementable, okay? So let me just introduce a bit of notation, which is probably familiar. It's very similar to the kinds of things that we've seen in prior talks. So I'll write do v to indicate performing an effect, and we're going to pass a value up to the handler. And then handle B is the body, and H is going to be a lambda that's going to accept a value describing the effect, and also a continuation. Okay. Now, why would we want to use effect handlers other than they're great? Well, why are they great? One reason is it's a uniform means of expressing lots and lots of different kinds of effects. So if we're trying to build a model that's going to be able to express all of those different systems that I've shown, I want something that's pretty generic. And so effect handlers are one way of doing that. If I just have a base model with effect handlers, I don't have to think about, do I want this specific effect or do I want this other kind? We can just have effect handlers, and that's enough. Okay, well, that's maybe more a general reason, but there's a more specific technical reason why we're using effect handlers in this work. And that's because in order to get this erasure property, I need to distinguish between effects that are performed in two different contexts. So I need to say there's a certain kind of handler that is going to handle effects that are performed in your main program, in your normal execution. And I'm going to have a different kind of handler that is going to handle effects that occur in the extent of contract checking code. And these two don't interact with each other. So it will just, if you have an effect that's performed in ordinary code and you have a contract handler around it, it will just bubble through sort of normally. Okay, so that's the key technical device that we need in order to get this erasure, or one of the key technical devices to get this erasure theorem. Okay, so I want to give a little example of this. So suppose you have map, and you give it a function and a list, and you're mapping the function over the list. We're very familiar with this. And I'm going to show you the contract for on f, which is a function, in this case, anything to anything. But the interesting part about this is I want to guarantee that you use this function at most n times, where n is the length of the list. Okay, so there's some dependency going on here. And the contract that we'll implement is this use at most n times contract. And we're going to need an effect for this. Okay? So it's a bit of a generalization, I guess, of the interop example I gave earlier. Okay, so how are we going to do this? So suppose we have a function from x to y. And I have the ordinary function contract at the bottom with a normal arrow, x to y. But the additional thing that I'm going to do is I'm going to allocate a mutable reference that's going to contain the number of times that I'm allowed to call this function in the future. Okay? So the key thing to take note of here is this ref n, okay, a mutable reference that contains n. Okay, so then what do I do with this? Well, I need to ensure that when I apply this function, I'm going to make sure I don't go too low. All right, so I actually need an additional piece here on the domain. So instead of just x, I'm going to add an additional conjunct that says I can only use this n times, and the way I'm going to do that is I'm going to pass in this reference that I've allocated. Okay? Right, so now we've punted, and we have to define this max uses thing. And so this is going to do pretty much what you expect. We get in the reference. And this is going to be applied when you apply the function. And we're going to say, get me the value that's inside the reference. If it's 0, then that means that we've used this function too many times. So we're going to give back false, which means that the contract is going to fail. Okay, this is what we call a flat contract. It's just a predicate that says, yeah, you've called this too many times. Otherwise, we're going to update the value that's inside of the immutable reference and then give back true. So hopefully this is actually quite intuitive, and I think that's the idea. And one of the benefits of contracts is that even if you're checking something that's pretty sophisticated, perhaps, you can write these pretty easily. And I think programmers can write these quite easily. OK, so that's the implementation of the contracts. But of course, we're using effects. We're using mutable references. So we actually need to execute this in the context of some handler that's going to handle these operations. OK? So you can imagine that the entire program is going to be run inside of this run with mutable references in the side of this thunk. So you have a top-level handler, which is a pretty normal thing to do. And the key thing about this handler is that I have handle diamond, which is the contract effect handler, okay? Because we are performing effects in contract code, okay? So you would put the implementation of mutable references where the ... is. But there's one kind of funny thing about this, which is you have to constrain the kinds of handlers that you can put in here to satisfy erasure. So this is the second caveat about this design, is that if I did something like this, where I had a handler that just threw away the continuation, throwing away the whole program, that's going to violate erasure, okay? Because, well, certainly if you perform this effect in contract code and then you throw away the program, you're doing something different. So that's going to violate the property. So if we actually have to constrain these handlers in a certain way. And if you're interested in that, you can look at the paper in more detail. OK? So one other thing to mention is that it seems like, well, there's quite a few constraints here. And this is certainly true. We've tried to make this system a little bit more expressive. And it turns out that if you make it a little bit more expressive, you end up violating this erasure property. So we found a pretty unique design. We've gone as far, I think, as we can without violating the property. Okay, so that's just summarizing the two key technical ideas, is this distinction between main effect handlers and contract effect handlers, and an appropriate restriction on contract effect handlers. Okay, so just to sum up, in the paper we have more theory and more practice. So more theory, we have some more variations on kinds of contracts that perform effects, which we call main effect contracts and contract handler contracts. And those are used to implement various different kinds of contracts. And we have a blame correctness theorem, which is a kind of standard theorem that you prove of a contract system. So that holds for the one we've constructed. And then we have two implementations. One is a standalone hashlang that is a fully faithful implementation of the model. And then we also have an implementation that is in Racket itself, which is inspired by the paper, but is backwards compatible. So we've made a small adjustment to Racket's contract library that allows you to express some of these contracts. But we have to stay backwards compatible, so it's not fully faithful. And finally, an evaluation. So we actually use these implementations to implement toy versions of all those systems that I showed earlier. Okay? All right. Thank you very much.
Okay, so
hey, nice talk. There's been work on statically removing contracts from programs, like soft contract verification and work like that. Do these play well with this, or could they be extended to play well with this?
It's a very good question. I'm quite familiar with that work. And this is certainly something that we want to do in the future. And I think there's no reason that it couldn't apply to this other than we need some people to engineer it. But certainly, I think the techniques could apply. Yeah.
Thanks, Cameron. This is really nice. Could you say a bit more about what the restriction is on the handlers? I guess I have two particular use cases in mind. One, I imagine you don't allow multi-shot continuations.
Correct. Yep.
Right. And then two, do you allow anything, any kind of handler in which the continuations escape?
No. Yeah.
No.
So it's basically use exactly one in-tail position. It's quite restrictive. Yes.
Okay. Thanks.
And we would like maybe if we could relax that a bit, but we haven't figured out any way to relax it anymore.
Yeah, I guess the obvious one, I mean, one of the main uses for handlers is where you do some form of concurrency, and you only run your continuation linearly, but maybe not just yet.
Yeah.
You still don't let it escape as such, but yeah, I wonder if that could be useful or not.
Yeah, that would be interesting to think about. Yeah, certainly.
I've got a question from the Discord. In the bounded application contract, what do you gain from using an effect handler for state as opposed to a primitive mutable reference? Is it easier to restrict effect handlers so that they're well behaved?
So the point of using the effect handler is to really, for the purpose of a model and to prove this property. So certainly, if you were doing this in Racket, you can just use Racket's built-in mutable references, and that's perfectly okay. But for us, we're interested in proving this property and having it apply to all these systems. So in practice, yes, you can certainly just use built-in effects, and that's fine. But if you want to know that erasure holds, then effect handlers, I think, are the way to go. Yeah.
Got another question from the Discord. Do you have...
Maybe I can add on the previous question, and that's like, is this more expressive than state? Like, do you have other use cases?
Yeah, so basically all of the practical instances that we've found are state-like. So maybe not exactly global mutable references, but something kind of like that. And we are certainly interested in perhaps examples that go beyond that. But certainly we haven't found any in the literature yet.
One more from the Discord. Do you have nice examples of contracts that use more power from control effects than just mutable state or continuation?
Yeah, so that's similar to that question. So, but we're interested in more, I think, is what I would say. Yeah.
Take one here, and then if you have more from Discord.
Hi, thanks for the great talk. A couple slides in, you had a sort of big line of checks of things that you could successfully do. One of them had a little asterisk on it. What's the asterisk?
Yep. Yes. Yes, I can say a little bit about that. So that particular paper had contracts, but those contracts actually violated a little bit of what we would, some of the, I guess, one of the principles we would say about contracts. And so it had expressive power that was a little bit beyond like normal kind of contracts. So that's why that asterisk is there. We can do it, but maybe a little bit less powerful than what they had in the original paper. But if you're interested in more specifics, we can talk later, certainly. Okay.
We need to switch speakers, so I guess we'll stop here, and there's more questions on Discord. You can take them later.
Thank you.